Let's see. Okay. Thank you very much for the introduction and welcome to this talk. This is a project that happened in collaboration between ETH Zurich and TU Delft, and it's called GravoTet, a fast multigrid hierarchy construction for tetrahedral meshes. Let's get right started. So we walk around Istanbul and we meet this octocat. And the first thing that comes to my mind is, can I tetrahedralize this and then solve a heat equation on it? So this cat is now not just a surface, it is a volume full of little tetrahedra. And typically when you try to solve something like this, a PDE with a Laplacian on a volumetric mesh, you would instinctively first try a direct solver, but direct solvers scale poorly. And when you have volumes, you get a lot of vertices on the inside. So the scaling becomes quickly very expensive. And the state of the art that often a lot of people use is called Holmot, for example, a sparse optimized solver. But even that will struggle poorly when the resolution goes into the million. And the first question we have is like, oh, is there a way to do this faster? And there has been for a while. These methods are often called multigrid methods, and they operate by working on different resolutions. So you have a sparse symmetric matrix system, and it's just AX equals B, and A is a sparse symmetric matrix, and you leverage the computation, like different methods for different resolutions. So you can focus your computation on the high resolution details using something like Gauss-Seidel iterations, which converges poorly globally, but converges well when you just try to reduce the high frequency error. So you go to the high resolution to reduce the high frequency error using Gauss-Seidel, and then you go to the medium resolution, and then you can focus on those frequencies to resolve. And then you can continue this until you go to a very low res, and there the scaling problem that you had at the beginning with the too high resolution to use a direct solver doesn't happen anymore, and there you can use a direct solver. And generally in multigrid methods, you then want to communicate between these different resolutions. And the basic algorithm is called the V-cycle algorithm because you travel down and up and then down and up and down and up again, this hierarchy, and you pass on the residual, which is called residual. It's basically the error. You pass it down, you solve it, then you pass it up again. And the main ingredient for a multigrid method is the so-called prolongation matrix. The prolongation matrix tells you how to map the values of one level to the next level. And also the transpose of the prolongation matrix tells you how to map the higher level to the lower level again. So it's basically interpolation, extrapolation. And it's a series of matrix, one matrix for each level transition. And if you take the original matrix system, you can just slap on the left and on the right a prolongation matrix. And then you're reducing your big matrix to a smaller space. And then you can continue working on that. And you do this for every level. So the key ingredient is prolongation matrices, and they are not unique. You can have many different multigrid methods giving you different prolongation matrices. And some of them can be like designed to just have very few levels. You can have a lot of levels of hierarchy. You can have different weights on how you represent the higher level on the lower interpolations. And there's a lot of freedom to do. But generally, there is also a lot of difference how fast these algorithm converges based on how good your choices of these prolongation matrices are. And this is what we want to do. We want to find good prolongation matrices. So we have a 3D volume that we want to use multigrid on. And there are different approaches to deal with 3D multigrid. Very basic, popular, and awesome are grid-based methods, but they are not suitable for representing the curved surfaces when you are reducing the resolution. So on your high-res resolution, you can use a lot of cubes to represent your curved surface, but then you go lower, 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 and at the bottom, you still want a good representation. And this is not going to fit well with cubes. Next are graph-based methods. So they use the connectivity of the mesh, and they're already much better. And also our closest related work is going to be a graph-based method that we're going to work with. But generally, they will, as we will show, converge slower. And then there's a third class that is directly designed for tetrahedral meshes. The problem is that they work mostly on edge collapsing and then repairing the broken tetrahedra that you get once you collapse. And we do not compare against them because they take hours for the meshes we are trying to use, while we are trying to build the prolongation and solve it within seconds. So what we want is fast construction of prolongation matrices and good convergence. And yes, we can actually do that by introducing our new method, GravoTet. GravoTet means graph Voronoi tetrahedral multigrid method. And it's a fast and effective coarsening strategy. That is the idea behind it. And it starts by having a prioritized sampling of what vertices do we take into the next coarse level. After that, we focus on the surface, because the surface is where we have more details, where the boundary condition is supposed to survive. So we give the surface extra attention. We do a approximately Delaunay connectivity on the surface. I'll explain that soon. And then we continue to the interior. Once the surface is established, we can then connect the interior of the our subsampling, our hierarchy. And after we have done that, we have like a set of tetrahedra, and then we can compute the barycentric weights to actually get the prolongation matrices. So let's go into some details. The prioritized fast disk sampling, we do it by first computing a feature on every vertex. So for example, a corner of the cube will have a strong variation of its normal around it, and then we give it a higher value because of that, and then we will sample it first. This will be a prioritized vertex. We call it like, oh, this is an important vertex, so we should make sure it doesn't get lost during the sampling. So edges of a cube would survive, or tips of the ear would survive this way. And then we sort all the surface vertices by these features in order for the fast disk sampling to then start with the important vertices. And the basic method of the fast disk sampling is take a vertex, build a radius, and instead of querying for the nearest points, we simply look at the neighbors in a 2-ring at max. And then if a vertex is too close, we say, no, remove you, go away, shoo shoo. These red marked crossed out vertices will not be part of the next coarse level. And then we continue this, we take the next vertex, we look at the radius, we start removing more vertices. And this is very fast, linear time. And speed is something that we really need in order for our goal to be reached, to have fast results. So we end up with 5, in this example, 5 coarse vertices that go into the next mesh generation. And an added bonus, because we sorted the important vertices first, and then we sampled them first, the next coarse resolution already has the same ordering preserved. So the important vertices stay in the front for the next generation after. And now to the core idea. We have heard this now plenty of times. Voronoi diagrams dual create Delaunay connectivity. Delaunay connectivity is our favorite type of connectivity. It makes very nice meshes. But getting actual Voronoi diagram Euclideanly takes some more effort. And we avoid that effort by going for a graph Voronoi diagram that we can quickly compute using the connectivity we just had. And then we just take the dual of that and assume that this is good enough. It's not going to be perfectly Delaunay, but we will see that the properties it has in its barycentric weights are good enough. I mean, actually very efficient for multigrid method. So how do we do this? The clustering part now. So we have these orange vertices. We want to connect them with each other. And a straightforward way to do this is to look at the fine vertices, so the green ones, and look at where are they connecting. If every green vertex has a closest coarse orange vertex, and if two green vertices are connected that belong to different coarse vertices, we connect the coarse vertices. So it's something you can do fast with Dijkstra's algorithm, and starting multiple locations at once, you can quickly scan which vertices belong to which coarse mesh and coarse vertex, and then connect them with each other, and then you get something like this. Also very fast. And we start by only doing this for the surface vertices. So we had sampled all the vertices with prioritization for the surface, and then we connect the surface vertices, and then only after that we go into the volume. And the reason why we're doing this is if you don't, then you end up with this type of mesh, and it should make you feel weird in your stomach when you see it, because the surface is all blah, 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 because it wasn't taken care of, prioritized. And this is why I'm doing the other way. We get this nice surface, and we need the nice surface on the coarse resolution because our boundary value problem is defined on the surface. And if the surface at the bottom is all mushy, then we cannot expect good convergence of our solution. Once we have that, so imagine you had all this in 2D. Now we can go into 3D. So the surface will now grow into the interior of the volume. And with the exact same connectivity rules, we just continue, and then we have all the vertices connected. And then we want to compute the prolongation matrix weights. So what we do then is we look at the coarse vertex connectivity. We look at every fine vertex, for example, this green one, and then we ask, in which tetrahedra are you inside of? And that's a quick test of looking at the neighboring vertices, finding the coarse vertices, and checking, are you inside of it? And then you take the barycenter coordinates of the green point relative to the tetrahedra that it's inside of, and those will be your prolongation weights. So those are the parameters of interpolation that you then use in your multigrid steps. And notice, though, that because we used a graph Voronoi, we're not actually getting exact tetrahedra. Many of them will be fine tetrahedra, but they may overlap, and they may even collapse. And it is actually okay. Don't be afraid of collapsing tetrahedra when you're doing only barycentric computations. You're not computing the inverse mass matrix, because that would explode, but you're just having a tetrahedra that might collapse into a triangle, but the barycentric interpolation is still reasonable in that. So, and then this is a repeated. So we do this once to get to a lower resolution, and then we can do it again to get an even lower resolution. And generally we stop once we are below 10,000 vertices, and the tetrahedra that come out are all reasonably shaped. They are nicely spaced away from each other because the vertices were selected using fast disk sampling to be in a nice distance from each other. And then we can run our algorithms on this. So for example, 500,000 vertices in the input, and then we can compare our method together with, wait, this is the green one. This is a graph-based method, and these are the other two ones are algebraic multigrid methods. The algebraic multigrid methods only care about the matrix. The graph-based method, oh, sorry. Okay, I shouldn't use this. The graph-based method uses the connectivity of the mesh, and then our method uses the barycentric weights. And we see from the total computation time that the actual build time of ours is bigger. It takes more time to build up, but the solving time, it's much faster. And this is sort of the benefit of having better prolongation matrices, putting more attention into building them. And then the direct solver at this resolution is still competitive for Poisson problems. Then we can look at biharmonic problems, which are inherently more ill-conditioned. And there we can see that our method's added convergence quality is really beneficial for this, while the other methods really struggle. to get anywhere close to the tolerance. And the direct solver still holds up for this resolution, but we can now up the resolution, like, oof, give me more. And we end up, for example, with 2.8 million vertices as the input TET mesh. And then our method still continues to do well for the Poisson problem, while the direct solver fails because it's very memory intensive and scales poorly. It already starts to fail on my machine at 800,000 vertices. And then the graph-based method is still doing fine, but then let's look at the biharmonic problem, and there the competition stops. Most methods really converge poorly or would take almost forever, while the direct solver also has no chance for this resolution, and our method still holds up. And as you can see, most of the computation time now goes into the solving itself. The buildup is now minimal. Yeah. We have tested this on plenty of meshes for performance. And in generally, after 100,000, 200,000 vertices, our method starts to beat, not just in build time, but in total time. So this is important because a lot of multigrid methods are designed to solve faster, but the build time is sort of considered to be separate because they think of, oh, I want to run a thermal simulation, so I only need to build once and then I solve all the time. What I'm presenting here is something that where the build time with the solver time is actually together very nice. And for the biharmonic problem, the competition ends earlier. Many methods time out, or the Holmot has problems. Direct solvers fails at already 800,000 vertices. And yeah, that would be my presentation. I have more slides, but I had some time pressure. And you can ask me about mesh quality and ablation study and sparsity if you want to. Thank you very much. Yes. Wow, what a great question. I love it. Let's look at the mesh quality. So here you can see two examples, the armadillo and the fertility mesh that I used in the presentation. Laser. Yes. So the red curve is the input. It was generated using TETGen because FTET just couldn't finish at that resolution. So I stuck to TETGen, and you can see, okay, the minimum dihedral angle, yeah, this is a good quality mesh. And once you do the method apply, you get these orange, green, blue, these other curves, and they all look quite similar. They all have more of the very thin slices, but consistently. Like if you continue the algorithm, it doesn't keep moving to the poorer and poorer quality. And here on the right, we see the aspect ratio. So some of them are like super thin and then they explode here. But generally, like, yeah, the red ones are better. And then we shift a bit to the right and the aspect ratio, but it's not too bad. Here are some more examples if you want to see, including Istanbul OctoCAD. Great. Wonderful. I love it. How fast does the solver converge? Okay, let's go to, yeah, it's an iterative solver. So here you see the time. So first you have the hierarchy building. This is the building of the prolongation matrices. This part is so small that you cannot see it, but here you have it, 10 seconds. It's the same for the Poisson and the biharmonic problem. And then you have this 29 seconds. This is the setup of the hierarchies. So remember that for the multigrid algorithm, you have to multiply some matrices together. That step takes some time as well, but you only have to do it once. And then after you have done that, you just do the iteration, V cycle, down the resolution, up the resolution, down the resolution, up the resolution. And this is the time that goes in here. So for 2.8 million vertices, the biharmonic problem on this fertility mesh took 36 iterations. So these are the dots that you see here. And the total time is 164 seconds, which is about so to us so comparing to the others, the biharmonic one was the hard problem to approach, while the Poisson problem was the easy one and the more common one. So we wanted to go for the biharmonic as well because this is the harder one. I haven't tried even harder problems than that. But notice also that for the biharmonic problem, the relative residual is like the target is 10 to the minus 5, while for the Poisson problem, it's 10 to the minus 8, because people usually are sufficient when they try to solve the ill-conditioned problem with less accuracy. Okay, pleasure. Good question. That actually was a problem in the paper. Uh, that we had a input mesh that we wanted to TET-gen, and then the mesh was broken, which I didn't notice. Then the TET-gen was broken, and then it didn't converge well, and it took forever. I was like, what is going on here? And then I had to repair the mesh first to make it watertight. But generally, I relied on TET-gen to get these high resolution meshes, and trying to add some noise without inverting something was, yeah, not the data. Yeah. 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 Yeah, that's true. True. So the input mesh is the only input like quality TET mesh that we care about. And if that one is broken, then the Poisson problem is broken as well, because then you have these negative masses, or the mass matrix has these extremely large values. So I haven't, like, I trusted TET-gen, but if I imagine that we would now break one of these TETs, then we couldn't expect any of the solvers to work on this. So my answer would be, yeah, we have to, by baseline, require good quality TETs.
Okay. Hello, everyone. I'm Serkan Demirci. I'm a graduate student at Bilkent University, and I'm going to present our work, direct volume rendering of tree-based tetrahedral adaptive mesh refinement data. So, first of all, some prior background information about direct volume rendering. So, when we talk about direct volume rendering, what we are trying to do is to convert 3D volumetric data into a 2D image directly from the data without creating some intermediate surfaces or some other types. And when we define volume, everyone knows we can say it's a quantities or defined over a 3D domain. So when we for that direct volume rendering, there is usually two steps. First one is the sampling. Sampling means that we take we acquire the scalar from a position. Then we use classification where we take that scalar and convert it into a color and density value. There are many different rendering algorithms, but the ray marching is well known and simplest and common one. So in ray marching, we take some fixed steps throughout the volume. Then we take samples, map them to colors, then composite them into a color. And more recently, we have is starting to get more popular is woodcock or delta tracking. So for woodcock or delta tracking, we have it's a Monte Carlo's integration method. So if it's a homogeneous volume, we know how to solve it with Monte Carlo integration. But it's not usually, the volumes are not homogeneous. So what we do is we pretend as if homogeneous by adding some fictitious particles. Then, so our volume becomes a homogeneous volume with a maximum density is becomes this density. Then we randomly go based on the maximum density. We sample some distance and go there, take a sample. Then we say, what is the probability of that particle being the real or fictitious particle? And using that probability, we decide, we actually throw a dice and we decide whether we call it fictitious or real particle. And if it's fictitious, we continue because we didn't hit anywhere. If you decide we hit a real particle, we return its color. Similar to many delta tracking methods, similar to many Monte Carlo integration methods, this method usually is much faster, but requires many samples to be taken and averaged. So we get some color value and we apply this process over and over again, and finally it can, when we take all the averages, when we take the average of all samples, we in the end get we converge to unbiased, correct solution. So again, to repeat it again, when we say volumetric representations, it's a quantities defined over a 3D domain. Most commonly used representations are structured mesh, unstructured mesh, and adaptive mesh refinement. Structured mesh is the most simplest one. We divide the domain into a fixed size voxels, and however, it has some problems if the volume is too not homogeneous, non-homogeneous, and if some part of the volume requires high frequency features and other parts do not, we base some memory and computation over them. Also, for simulation, if we use structured mesh, it doesn't conform to the our domain. So that's another problem. So unstructured meshes are another method. So we divide the space into polytopes, usually tetrahedral or hexahedral, and we use that to perform the simulation and or represent the volume. So unstructured meshes are good for representing the input simulation domain or geometries, but again, they do not adaptively refine when you do the simulation. And adaptive mesh refinement is similar structured meshes, but we start with a coarse mesh and we progressively refine some cells. And adaptive mesh refinements are good for progressively refining it during the simulation, but they do not, again, follow the input geometry for simulations. So to solve these two problems, one is the try to conform to the input geometry, and the other one is the try to adaptively refine the volume during the rendering. Holke proposed AMRs with general element types. These have some coarse unstructured meshes, then they are refined progressively. So in our work, we focus on tetrahedral AMR meshes, specifically TET-AMRs. So it's composed of an unstructured TET mesh, where each element can be further recursively refined into 8 children. So it becomes a forest of refinement trees. Each coarse element has a tree, essentially. So we get, during the simulation, we refine or coarsen the volume based on the our simulation criteria. And one thing good about this structure is that so you don't need to store all of the vertices of the finer levels, because they can be deduced from the coarse mesh. So Holke only stores the coarse mesh and some compact lift descriptions that can be used for recalculating the vertices. So there are no existing rendering methods for directly rendering TET-AMR. One method to render this kind of data type is to convert it into an unstructured mesh. However, this means that we are adding new vertices and we are increasing the memory size. Also, we are losing the hierarchical information for the volume. So in this work, we proposed direct rendering of TET-AMR data. We realized this rendering with 2 methods, Demirci and woodcut rendering. And we propose some refinement tree traversal methods. And instead of generating the vertices, we on the fly generate the vertices as we traverse the finer levels. And since we have a hierarchical structure, unlike the unstructured converting to unstructured mesh, we can do some performance improvements. We experimented on 2 methods. One is coarse mesh macro cells. The other one is the view-dependent early tree traversal terminations, which is something similar to level of detail. Okay. So we start with the preprocessing. Unlike Holke, we also stored the non-leaf element descriptions because it's faster to rendering for that. It's faster to rendering that way. Also, we reorder the elements in pre-order arrangements to again speed up the rendering. Also, the child orders we changed a little bit. So when we are talking about rendering consists of 2 stages. The first one is coarse mesh traversal, where we traverse the coarse mesh one at a time. And using a rendering algorithm, we decide where to take samples, and we take the samples. So to take samples from that volume, you need to go down to the leaf element and create the leaf element vertices and interpolate the vertex scalars. So for that, we use refinement tree traversal. So for, again, coarse mesh traversal, we use hardware BVH over the tetrahedral faces. This is for modern GPUs that have the ray tracing cores. So we can offload the work of finding the next tetrahedron to another core during the rendering. So it's faster to do it this way. Also, for that, we send 2 rays. One is back face culling enabled ray, and the other one is front face culling enabled rays. By how they intersect with the faces, we determine whether we are outside the mesh or we are inside one of the tetrahedron and we are going towards another one, and we are exiting the phase, exiting the volume. These correspond to case 1, 2, and 3. So rendering refinement tree traversal. So our aim in here is to, given a point, we find out which element we need to go, we need to traverse along the tree, and we need to calculate the ID and the vertices of that element. So for this, we need to identify the child elements. We use 3 tests for identifying the 8 child elements, children elements. First, we determine whether the sampling point is on the top left or right back of half of the current tetrahedron. Then second one is left, right, or top back halves, and the third one is the inner and outer parts. So in order to identify these elements, we try 2 techniques. The most simple one is the point plane orientation test. So for each half test, we require 2 orientation tests and 2 plane point orientation tests. And for the inner outer test, we need 4 inner outer point orientation tests, so 6 total orientation tests. And we also tried barycentric coordinate-based test. It simply uses the barycentric coordinates to do the same plane test. But since we know the barycentric coordinates, we can do this with simple arithmetic comparisons and additions, very simple ones. So this, however, requires 4 cross products for barycentric coordinates. We experimented on this too, and usually they are really close to in terms of performance. So one performance improvement we tried in for our rendering method is macro cells, coarse mesh macro cells. So macro cell is usually used in rendering to speed up the rendering. And a macro cell is a low resolution volume that's built over the volume data, and it stores the maximum densities inside each part of the volume. So what we do is traverse the volume, traverse the macro cells, and use this maximum densities to either in ray marching skip the macro cells, or for woodcock we homogenize the local volume so that it's more tight to the real volume. Generally, this data structured grid is used for that. But we said, what if we use the existing coarse mesh as a macro cell? Since we are already traversing the coarse mesh to identify the elements, so we tried this, and it also aligns with the theta-MR mesh better. And the second one is the view-dependent early tree traversal termination. So essentially, we stop the traversal when the element gets too small on the screen, and sample that element instead of one of its child or leaf elements. So quickly going over the experiments. We use TET code library for generating these volumes, and we synthesize some test data with different scenarios. We take, for example, heptane's data is from structured mesh, but Agulhas is unstructured mesh. So we changed some sources of our data to make it generate some interesting various scenarios. And advection is we didn't synthesize that. It's a simulation. Advection simulation comes from an advection simulation. So if you look at the statistics of our data, they differ a lot, and usually average refinement levels are different. Their number of coarse elements are different. So they are represent different cases. So if we look at the performance between our TTMR rendering and unstructured based rendering, for ray marching, we are most of the time faster than the unstructured mesh render, except for the advection test, advection data. This is because advection has small number of coarse elements and very deep refinement levels. Here, we waste time for tracing rays on the ray tracing course, and that's why it's a little bit slower. And for woodcock, so for woodcock, similar story, but here Agulhas set is a little bit slower, and this is because for the other reason. So we are now wasting some time on tree traversals instead of using the hardware BVH. And for memory, when we look at the memory, we get maybe sometimes up to 2 times, a little bit more 2 times compression. So our experiments, so for course macro cells, we have similar story like this. So everything is faster except for Agulhas set. This is because Agulhas have a lot of coarse meshes and are always trying to test those test for those coarse meshes whether that coarse mesh is empty or not. So it slows down the. And for woodcock, there is a interesting result. So for woodcock, for Agulhas set, it comes much more coarse macro cell becomes too much slower. This is because we have a lot of trees, and for woodcock, if you have a lot of macro cells, you have to go back and each time restart the rendering. So this slows down the rendering time. So we have dependent early tree traversal termination, and we tried with some threshold values. As we increase the threshold, we get more. We terminate the trees from higher up, so less depth, and you can see we are speeding up the rendering, but we are losing some of the details. It is same for woodcock, but for woodcock we are getting less benefit from early tree traversal because woodcock takes less samples on average. So here's the plot of it, and so we start with early termination off. Then when we enable it, we need to do some area calculation that slows down the performance, and as we increase it, we get some performance back. This is not possible with the unstructured mesh renderer because we don't have a refinement levels or hierarchy. So, and quickly conclusion. So we propose a direct volume render for the TTMR data, and we avoid explicitly constructing the unstructured mesh, and it achieves faster rendering times most of the time and reduce the GPU usage. And for future work, maybe extending our work with other AMR element types, and maybe some data parallel rendering can be used. Thank you for listening. So far, is there at least one question? Is for what substrates when it falls into this structure one by in and and
Hello, everyone. I'm Gowtham. I'm here to present Vox to Serve, a faithful surface extraction from coarse binary voxels. Intuitive tools for creating shapes using voxels have gained a lot of popularity in recent years. These tools allow users to place blocks in a regular 3D grid to create shapes, and this has allowed users without any 3D modeling experience to create complex shapes easily. And also games like Minecraft and building block systems like Lego are using this concept to build 3D structures. So our motivation comes from large quantities of the readily available data from various sources. But these voxel representations only provide abstract or low resolution approximation of shapes. They lack realism. They fail to meet typical modeling or rendering applications. So, how to convert these boxy looking meshes to regular smooth meshes without losing much details? Reconstructing piecewise smooth geometry has been well explored in 2D. For instance, in Polyfit, they vectorize low resolution images, raster images by perceptually fitting polygons. And in another work, an 8-bit art is processed using specific mask spring system to relax pixels to generate vectorized outputs. In 3D, the traditional methods like marching cubes and dual contouring, and there are several variants, typically assume surface to be smooth. Uh, they either uh, they either classify they either classify the corners of a cell using a lookup table or place a vertex based on a error function. They usually result in a uniformly blocky surface with soft, not so sharp edges. While recent neural variants primarily focus on alternate representations, neural marching cube and neural dual contouring accepts binary voxels to be their input. They noticeably improve their respective prior art, but they still target higher resolution content, that is 128 cube or more, and they also still rely purely on local context. So their outputs often diverge from viewer expectations and produce unintended sharp features or suppress intended sharp ones. So we introduce Vox to Surf, a novel method to reconstruct feature preserving piecewise smooth surfaces from binary voxel grids. Our method automatically converts voxels to voxels into piecewise smooth shapes while preserving viewer intended sharp features. But mathematically, all the edges of a voxel surface are sharp, but only a few appear to be sharp to the viewer. We address this challenge in three main steps. First is to predict the user intended sharp voxels using a deep deep learning based classifier. Then use these identified sharp voxels to create a sharp feature curve network, and later optimize the curve network and the proxy surface between the smooth curve network. In the learning step, we use a SwinUNetR based transformer network to create a coarse probability mask, um, followed by a custom made refinement module which focuses on local details. This outputs a 64 cube probability map. We chose SwinUNetR because it is useful in capturing um, long-range global 3D context, and the refinement module will focus on the focus on correcting local mistakes that may have been missed in the first stage. So in this way, the final prediction gets to keep global context from SwinUNetR and also becomes more accurate at local voxel level. So our learning step results in a heat map showing confidence of the prediction. We classify high confidence voxels as sharp. Now we need to convert this set of sharp voxels into coherent network of sharp feature curves. We do that by applying the linear triangulation on the sharp voxel centers and prune the longer edges. We can actually formulate this as a 2D reconstruction problem, representing each voxel center to be a vertex in 3D, uh, seeking a curve network. Since the curve network is made by connecting sharp voxel centers, we need to project it to its corresponding proxy surface. And we know that our voxel grid is a binary occupancy grid, which is 0 if it is empty, 1 if the surface is present. We create square faces adjacent to zeros and ones, aligning to the horizontal and vertical axis. And then we project the curve network extracted from the previous step onto this proxy surface by following set of rules. This results in a curve network in terms of mesh vertices. Now we smoothen this blocky curve network by using a mass spring system. We place uniform masses at each of the vertices and consider each edge to be a spring. And we use a smaller rest length than the current edge length to and begin the simulation. As the simulation progresses, the tension forces tend to better align the vertices, creating a smoothing effect. And throughout the simulation process, we constrain the future extremities. Those are degree 1 and degree 3 vertices. This helps us to preserve the features. We also employ weak positional constraints, allowing vertices to not move more than a voxel diagonal length from its initial position. And also, in addition to this, we do a um, final inflation mechanism to prevent any over shrinkage of under constrained closed loops. This results in a smooth curve network which acts as a basis for mesh smoothing. Similar to the curve network simulation, we associate a mapping system to the triangulated proxy mesh. This involves assigning um, uniform masses at vertices and considering edges as damp springs. We also use, similarly, we also use shorter edge lengths to start the simulation under tension. And the simulated curves the corresponding positions on the mesh acts as the constraint, hard positional constraint, and we let the simulation begin under tension. This results in our final smooth mesh with user intended sharp features. Our method successfully reconstructs a wide variety of shapes from ABC dataset, and we also try to generate shapes. We also try to create shapes from organic shapes. Uh, they work well, and we manually created voxel grids depicting few shapes and tried our method along with several alternatives. And we found that our method to be working fine, better than the rest. So to conclude, in this work, we tackled an underexplored problem of perceptually reconstructing surface from a coarse voxel sets. Our solution combines learning and geometry processing steps to um, best solve the problem and outperforms the potential alternate methods like NMC or NDC. So our learning step currently depend on ABC dataset. Improving sharp voxel detection could be an important direction in our future work so that we can handle more organic shapes. Since we do not explicitly check for self-intersections, our method might produce some, but generally do not produce some self-intersections. Yes, thank you. Yes, of course. It is fairly easy to extend if you have a colored voxel mesh, we can, because at the end we are simulating or smoothing the voxel mesh, we can use the color, the corresponding color on the mesh. We could definitely try that. Yes. So our during our learning step, so, our learning step produces a probability mask, which tells us which voxel represents a sharp feature, which voxel, I mean, it's a probability of being the voxel being sharp or not. Manually take them. Yeah. No, no, no. The ABC dataset provides sharp features. So yeah, we train on ABC dataset.
There's a star, a small one. This is hanging on. It's very important. They have been trying to do this for decades.
Yeah.
And looked to what they've been doing. Space system is working on.
I think it could be relevant, but initially we initially we thought um, how a result. I mean, the result is mainly how the user perceives it to be than the ground truth is. So in a medical application, the accuracy or the chamfer compared to ground truth has to be better than the voxel representation. So for us, how user depicts a voxel surface is is our more primary aim.
Precious, fully organic.
Yeah.
Thank you so much. Is now the framework still lost and
Stable.
Hello, folks. I'm Jinesh from IIT Mandi, which is located in the foothills of the mighty Himalayas in the India. And before I begin, I would like to thank the organizers of the conference and the reviewers for their detailed and constructive feedback. This talk is about an algorithmic framework for subvolume computation. And here is the outline. So we'll first formulate the problem, then we will formulate the envelope condition, which is then used to first compute the wireframe of the output and then the faces of the output. And doing so requires a study of the change of the topology of the envelope with time. And then I will show some results. The problem of swept volume computation is a classic one in solid modeling. Yeah. So given a solid and a motion, the problem is to compute the shape swept by the solid as it moves along the motion. Yeah. And there are a number of applications of this problem. For example, in CNC machining verification, one may compute the swept volume of the tool, yeah, and subtract that from the block and compare the resulting shape with the desired shape. While designing gears, one may compute the swept volume of one of the gears along the relative motion between the two gears and subtract that swept volume from a block to obtain the shape of the second gear. Yeah. In collision detection, again, you have a pair of moving objects, and you could compute the swept volume of one of the objects. Let's call it A, and along the relative motion between the two objects and checked the intersection of the same with the second object to detect collisions. Yeah. Of course, now there are many applications, but the real motivation behind doing swept volumes is that it's pretty. Um, Now, this problem has been well studied. There have been decades of research in this area, and but when it comes to CAD applications, yeah, there are two main requirements. One is um, a high degree of numerical precision and a guarantee of topological completeness. And to the best of our knowledge, the previous works do not address these two requirements. Moreover, I am not aware of any general implementation of solid sweeps in any CAD modeling software. And in order to address the aforementioned issues, in our work, we resort to algebraic modeling of the underlying constraints, yeah, which are then solved using subdivision-based solvers. These solvers, in turn, provide guarantees of numerical precision and topological completeness. Further, we have a boundary first computational approach, which leads to a robust algorithm. Right. Now, to get started in earnest, the input has two parts. The first is a solid, which will denote by H, and we use the industry standard boundary representation or BREP for its for representing H. Yeah. So in the BREP format, a solid is represented by its boundary, and this boundary may be composed of a number of faces which meet either with G1 or G1 or G2 continuity and so on. Yeah. Now a face is obtained by trimming the underlying parametric surface by a sequence of co-edges. Yeah. So, for example, this magenta face is bound by four co-edges. Yeah. And in this work, we assume that all the faces, all the surfaces, and all the co-edges, they are all represented by B splines. Yeah. We also assume that any pair of surfaces can meet with G0 continuity. So which means there is a sharp edge wherever two faces meet. Okay. Now the second part of input is the motion M, which is denoted by M, and it's a one parameter family of rigid motions. So which means that for each time t in this sweep interval 0, 1, there is a 3 by 3 rotation matrix AT and a translation vector B of t in R3. So that under the influence of M, a point X is transformed as ATX plus BT. And we again use B splines in order to represent AT and BT. Now, given H and M, the swept volume H plus M is this infinite union of all the translates of H along M. Yeah. So this H of t denotes the translate of H at time t. Yeah. So by definition, the swept volume is a solid. And we again want to use the BREP format in order to represent the swept volume. So which means the problem essentially is to compute the boundary of the swept volume. Yeah. Yeah, the well-known envelope condition forms the basis of our method. Yeah, and this condition, this envelope condition, gives a necessary condition for a point to belong to the boundary of the swept volume. It says that as this solid H is moving along M, yeah, a point P on the boundary of H will belong to the boundary of the swept volume only if the velocity at P is tangent to solid at that point. Okay. Or in other words, the velocity is orthogonal to normal at that point. And this is exactly what is captured by this function f, which is defined on the UVT space. Here UV are the parameters of the surface H, of the surface S, which forms the boundary of H, and T is the time, that is a parameter of the motion. Yeah. So F of UVT is simply the dot product of normal at UVT and the velocity at UVT. Yeah. And so we are interested in the zero set of this function F. And that is this. Yeah. What we're interested in. And the set of points which satisfy this equation will be called the envelope set. Okay. And of course, at the starting at the ending time, at time t equal to 0 and t equal to 1, this equality becomes inequality. And that set is called the end caps. But this is the easy part, and we won't focus on this, but we'll focus on computing the envelope itself. Okay. So in the swept volume example shown earlier, this example, these are the two end caps. Yeah. And this is a envelope, which will denote by cal E. And like I said, this is the easy part because it comes from solid itself. So we will focus on constructing of the envelope. Yeah. In this work, we assume that the envelope is free of self-intersections. Okay. What that means is that the union of the end caps and the envelope is the boundary of the swept volume. So now we will focus on computing this envelope itself. So at a high level, our approach involves uh, computing this envelope by computing sections of this envelope at a few time instance and then fitting a surface through those curves. So section of an envelope of the envelope at any given time t will be called a curve of contact at t. It is simply the subset of the envelope for a fixed time t. Okay, and in the previous literature, this has been also referred to as a characteristic curve at t. So in this example, you can see the curves of contact at a few time instances. Yeah, and the envelope is by definition the union of all these curves of contact E of t. So E of t is a curve of contact at t, and envelope is simply the union of all the curves of contact. Yeah. The output, yeah, has a natural VREP structure which is derived from that of the input. Okay. For instance, this magenta phase F here produce this magenta phase F sub E over here. This sharp edge, the colored gray, yeah, labeled E, it produced this phase E sub E over here, and so on. It's color coded. Okay. Of course, a phase may not generate anything on it. So this may be empty. Okay. In some, for example, uh, this phase did not generate, green phase did not produce anything over here. So further, so we will use this sub E. Yeah, we'll use this sub E in order to denote the geometric entity on the envelope, which was generated by the corresponding entity on the solid. So F produced F sub E, this E produced E sub E, and so on. Okay. So further, if you have a coedge C which bounds this face F, then this coedge C will generate a set of coedges on the envelope which bound the faces F. Yeah. Now these coedges CE will not only bound faces FE but also faces E sub E, where E was coinciding with C. Okay. So for example, if you look at this edge over here, yeah, this edge, it bounds face FE as well as the face E sub E. Yeah. Now this faces E sub E, they are also bound by the coedges generated by the sharp vertices that bound this edge E. But let's not get into details right now. Right. So now the construction of the envelope begins with constructing first the wireframe of the envelope. And by wireframe, I mean the co-edges, yeah, of the envelope. And so let again this C be a co-edge which bounds a face F over here. Yeah, let this be the face F, yeah. And let S be the underlying surface for F. So this co-edge C is specified in the parameter space of S UV as C of R equal to U bar of R and V bar of R, P curve, And in order to compute the co-edges generated by this co-edge C, yeah, that is, in order to compute C, we solve this system of three equations um, in four unknowns, yeah. So four unknowns are U, V, T, and R, yeah. So the first equation says that, okay, it satisfies the envelope condition, yeah, that a normal orthogonal to the velocity, that one, yeah. And these say that, okay, it actually follows this co-edge, yeah. And all these three are precisely represented using B-splines because all our input was in B-spline, if you remember. And so you have three equations and four unknowns. So the solution in general is one dimensional. That is a set of curves. Yeah. And we solve this using subdivision based solvers due to Barton et al. And this solver returns a set of polylines. Yeah. That is a set of connected sequence of points. But the important thing is that this solver gives two kinds of guarantees. It gives a guarantee of numerical precision, which means that each point returned by a solver is guaranteed to be within the prescribed numeric tolerance of the actual point on the envelope. The second guarantee it gives is that of topological completeness. So it guarantees to return all the solutions within prescribed a subdivision tolerance. Yeah. And it is through this that our algorithm gives guarantees of, you know, topological correctness and numerical precision. So in this example, you see this magenta face is bound by four co-edges, and they gave rise to these four co-edges, which are shown in a color-coded manner in the UVT space and also in the XYZ space. Yeah. Right. So now we come to the wireframe of the faces which are generated by the sharp edge E. Yeah. So let's say this sharp edge E lies in the intersection of faces F1 and F2, and the co-edges belonging to F1 and F2, which coincide with E, are C1 and C2. Okay. Moreover, E is bound by vertices V1 and V2. Yeah, these are sharp vertices. And like we said earlier, that the co-edges generated by C1 and C2 will bound faces E sub E. Yeah. And that computation we already described in the previous slide. And so now, in order to compute the co-edges generated by V1 and V2, we just use this. Yeah. So it's simply because it's sharp vertex. So it will trace a curve in R3. So that's what this is, albeit with appropriate trimming. Yeah. So for example, here, so C1, co-edge C1, that is a co-edge bound by yellow face, did not generate anything over here. The co-edge bound by F2 gave rise to this and this portion. The vertex V1 produced this, vertex V2 produced this. Yeah. Okay. So now that the wireframe has been constructed, we proceed to computing the surface information. Yeah. And like I said earlier, that this is done by computing a few curves of contact and then fitting a surface through them. Yeah. So now we want to compute curves of contact at a few sample time instance. So for a given time instant t naught, uh, the curve of contact is simply computed by solving this equation, right? Where uv belong to this surface, underlying surface S. So we are again working with this magenta phase, right? Which is underlying surface SUV. And so FUV T naught equal to 0. So here you have one equation and two unknowns. So again, you have, in general, the solution is a set of curves. And again, we solve this by the subdivision-based solver. And in this example, yeah, you see that a few curves of contact have been computed, and they are shown by these magenta curves. So let's say you computed n for n different time instances. You computed n curves of contact, and on each curve of contact, you obtained m points. So you have a rectangular grid of m by n points, which you use as a control point for fitting a B-spline surface, and which that surface is then trimmed by this wireframe, the co-edges which we already computed, right? And we are done. If only life were a bed of roses, because it is not, such things happen. Yeah. See, the topology of the curve of contact may change with time. And so, which means you do not have a regular or rectangular grid of m cross n points. So you cannot just go ahead and fit a B-spline surface. And this needs to be addressed, and this is how we do it. So that portion where the topology changes is shown magnified over here, yeah, in XYZ space, and the same is shown in the UVT space over here. And what is really happening is this, yeah. So at each time, the curve of contact has two components, but initially those curves go this way, and later they go that way. So essentially, you have a saddle point, yeah. And in order to handle such cases, we first need to locate such points where this topology changes. We call such points critical T points, and they are obtained by solving this set of equations: f equal to 0, fu equal to 0, and fv is equal to 0. The first equation says that, okay, this point belongs to the envelope. The last two equations say that the grad f, which is a normal to this surface in the UVT space, is parallel to the t direction. Yeah, and that's why this is happening. Yeah, so once you compute these critical T points, you get two kinds of points once you solve this. Yeah, in here, the envelope is hyperbolic at this critical T point. Here it is umbilic. Yeah, and these two cases are handled in a different manners, which means we need to classify the points as either hyperbolic or umbilic. And this is done by looking at, of course, looking at the Gaussian curvature of the envelope at this point. Yeah, and the sign of the Gaussian curvature will tell you whether it is hyperbolic or umbilic. And this function essentially computes the sign of the Gaussian curvature of the envelope. Yeah, and then you know what kind of point it is, and this is easily done. And so we won't discuss this. And in order to handle this, we simply split the envelope surface. Yeah, so the C is the critical T point. Yeah, and this curve of contact at that point is shown in black. The other curves of contact are shown in blue and green. Yeah. So what we do is this is a schematic only. Yeah. So these are the co-edges in the red. So we split the co-edges at this point A, E, D, and B. And from this curve of contact shown in black, we obtain these four segments. Yeah. So these four curve segments along with these co-edges gives you four loops. And these four loops, they've bound the four faces into which the envelope is split. Yeah, so you get four faces. And in this example, those four faces are shown here in four different colors. Okay. So concept is quite simple. You just want to split the envelope along this curve of contact at critical T point. Now, these critical T points may also appear on co-edges, not only inside faces. So for example, here, you see, there's a critical T point on this co-edge, which bounds the envelope face. And you see, initially you have two components of the curve of contact, but later you have just one component of the curve of contact. And this is again handled by splitting the envelope surface across this curve. Yeah. How much time do I have? 5 more minutes? -2. So then, so the concept is similar that you just split the envelope surface. So I'm going to skip that. Yeah. And here's an example. And this only summarizes what I just said. So let us skip that and instead let us impolitely stare at some results. And so here the input has about 4 to 6 faces, and this took about 10 seconds to compute. Some more examples. And here is an example which has self-intersections, yeah. So which are not been resolved. So input has about 17 faces and 45 sharp edges, and the output has 250 faces. This took about 20 seconds to compute. Okay, so I'll just conclude now by saying that this work raises more questions than it answers. The list of things it cannot do is longer than the list it can do, right? But of course, I won't present the entire list in the interest of time, but only the most important ones. The first is the self intersections. Yeah, they have to be handled. Then degenerate examples. So there are, we assume that the curves of contact are actually curves, but there are examples where a curve of contact may degenerate into a surface, which is not handled here, and such things to be handled. So let me stop now here in the interest of time. Yeah. Thank you. Michael. Yeah, so they are not identical, but they have the same sign. Yes. Yes, yes. Thank you.